Hi everyone, welcome to Incorporating Continuous Resilience in Your Development Ecosystem. My name is Curtis Reese and I'm a Principal Solutions Architect focused on app modernization here at AWS. And today you're going to learn about some of the most useful principles for building continuous resilience in your applications. So let's go ahead and get started. Now, downtime can be a pretty scary thing. Now, how many of you have experienced this scenario where something's down, people are screaming, and the users are basically being affected? Think back to the first time that may have happened to you. How did you feel? Did you feel like you knew everything that was needed to resolve it? Did you feel confident? I clearly remember my first outage, and I was terrified. I was a junior developer, and things were down, and people were screaming at me, trying to figure out why things were down, and it was a disaster. I had no idea what I was doing because honestly, in computer science, they don't train you for that. It's not something that you learn until you're actually out on the job. It took me an awful lot of time to figure out how to identify the issue and then actually go back and fix it. I didn't even know what I was looking for at the time. Now, today would probably only take me a few minutes to get a feel for what was wrong back then. It's always been a mystery to me as to why we don't get training on this. Like I said, we don't learn it in school, and most people only learn it once they're on a job. And I think I can speak for many of us. We learn the hard way. We learn in production. And have you ever wondered why an outage is so scary? One obvious reason is cost. These are the latest estimations from IDC and the Ponemon Institute. And on average, they say that an hour of downtime costs $100,000 to the business. And with those kinds of numbers, of course it's scary. That puts a lot of pressure on the business, and it puts a lot of pressure on you. And so think again back to that outage that you may have caused. How long did that last for? Let's see how easy it takes to get to 1 hour of downtime. If we look at this from an anatomy perspective, this is the anatomy of an outage. First, you have the detection phase. So this is that time where monitoring solutions, alarms, and escalation tools are starting to try and kick in. And that usually takes about 10 to 15 minutes. Then your team needs to go into the evaluation phase. They need to look at what's going on. That's where you start things like debugging and reading the logs and trying to really understand what is actually happening. So sometimes what it may seem like on the surface isn't actually what's happening underneath. But once you figure that out, then you move into the response phase. So applying the fix, patching the systems, things like that. And then you go into the recovery phase. So system recovery isn't instant. It's one of those things that can take quite a long time, and it needs to be progressively implemented and slow so that you don't have these yo-yo kind of effects. And finally, it's the confirmation phase. That's when we start asking and answering the questions, is the service fully back up and is it back to normal? So 1 hour of outage is actually really easy to hit. And as you can see, I've also plotted kind of the stress line. This isn't scientific, but it's something that we all feel. So as you go through the process through identification, through remediation, and through the phases of patching and fixing, you start to notice that there's that fear kind of towards the end of it. Why are folks scared once the outage is over? That's often when the fingers start getting pointed. That's often when you hear things like, that's your fault. Blame. So that's when folks like DevOps and architects start to fear for their jobs. And what is the reaction of people in the organization that experience fear? Well, typically they want to avoid it. And that's what we're going to kind of talk about here. Many organizations lack confidence in their IT services and fear failures. They often believe that failures are preventable and that they believe IT services are predictable and failures are caused by isolated changes. These organizations often focus on maximizing the return on investment for their current IT services and resist changes. These have led the development of robustness-centric risk management practices such as processes, rules, change management, change advisory boards, things like that, that are basically put in place to try and reduce the risk of failures. Now, frameworks like IDLE are a great example of this. They're really focused on trying to optimize for robustness. And these practices are often called risk management theater. They're based on the assumption that preventative controls on everyone can actually prevent anyone from making a mistake. So these are some of the practices that robustness-centric organizations put in place to reduce the risk of failure. The problem is that maximizing robustness often leaves an organization ill-equipped to deal with an actual failure. And as explained in the book, Resilience and Precarious Success, when an organization optimizes for robustness, it will underinvest. And I want to be that clear. They will actually underinvest in what we call non-functional requirements. Things like monitoring, things like telemetry, infrastructure support, and so on. In a previous job that I was at, things didn't fail very often, and so they took that as a sign that they could do things like turning off the logs on production because they were taking up too much space, turning off certain metrics because it was just noise. Those are the types of things that can occur and we want to avoid. It'll be considered acceptable largely because failures are expected to be rare. Unfortunately, it's naive to think like that. A production environment is basically a collection of unpredictable interactions between multiple different systems, and those interactions take place in unrepeatable conditions. So it's a complex system in which the cause of an event can only be understood in retrospect, which we often call hindsight bias. Werner Vogels, CTO of Amazon, famously said, "Failures are a given and everything will eventually fail over time." The truth is that in a production environment, it's in a perpetual state of failure. Richard Cook explains in his book How Complex Systems Fail. I quote, "The complexity of these systems makes it impossible for them to run without multiple flaws." Indeed, the fact that the production system often comprises of hundreds of dependencies, the probability is that something, somewhere, is actually in a state of failure. Organizations focusing on robustness encourage an attitude Sidney Dekker calls the bad apple theory. That's when a system is considered robust or reliable, except for the mistakes of its bad employees. When a failure occurs, the bad apple theory, often combined with this hindsight bias, often leads to a culture of blaming individuals. The attitude and culture discourages things that are important to the business itself, so it's very counterintuitive. It discourages things like learning, sharing, and collaboration, which is key for continuous improvement and thus key to resilience. So, how do we trade fear of failure for growth opportunity and improvement? Well, the answer is probably, you've guessed, to embrace failure and resilience. We don't want to fear failure. Simply put, resilience is the ability for a system to respond, absorb, adapt to, and eventually recover from an unexpected condition. In the book, The Resilience Engineering in Practice, Eric Hollnagel, I always mess up his name unfortunately, Eric Hollnagel and his colleagues break down resilience using a conceptual model known as the 4 cornerstones of resilience. So these are responding, so using things like automations to fix things when failures actually happen. There's monitoring, which is essentially observing the operational conditions, alerting when things go down or when things aren't acting the way that they typically should. We then have learning, and learning is understanding why failures have happened and how we can potentially recover from them in a safe environment. And then lastly, we have anticipate. And anticipate is basically combining the other 3 to understand what to expect and imagine potential failures in an attempt to prevent them in advance. So these are the cornerstones, and they're not linear. So please don't, I realize I have them in a line here, but they're not linear. The idea here is that they kind of build on each other more as like a Venn diagram. So designing for continuous resilience means creating an environment in which services can gracefully respond, absorb, adapt to, and eventually recover from unpredictable conditions, unexpected changes, and of course, withstand periods of failure. So I've listed some of what I believe are some of the most important and useful principles of building continuously resilient applications. I won't have time to dive into all of these. I mean, this is a lot, but I will provide some heterogeneous examples to help you get started moving towards continuous resilience. So let's start with anticipate. Like I said, these aren't linear. I'm going to go kind of like reverse, like what I feel is reverse order, but it'll make sense to you in the end. So probably the most important part of building a resilient system is reviewing and profiling the application. Code quality is important as it impacts the overall software quality, and quality impacts how safe, secure, and reliable your application is. High quality code is critical for resilience. Code is considered good if it does what it should, follows a consistent style, is easy to understand, is well documented, and lastly, can be tested. Amazon's internal team has used code reviewers and profilers on more than 30,000 applications. A few years ago, Amazon.com, in fact, implemented a code reviewer and code profiler during one of our biggest shopping days of the year, Prime Day. And in the process, we realized 325% efficiency gain, specifically on CPU utilization. And that basically lowered our costs by 39%. That's tens of millions of dollars in savings just on compute and infrastructure alone. And all we did was basically implement some simple profiling on the application to better understand how it was performing and make adjustments from there. So code reviews are important at each stage of the application lifecycle, both during the development and once an application is basically up and running. The tool used by Amazon.com in that previous example is actually accessible directly to anyone today from the AWS console, and it's called Amazon Code Guru. It's powered by managed machine learning that provides intelligent recommendations for improving code quality and identifying an application's most expensive lines of code. It scans for critical issues, helps you identify hard-to-find bugs, and also recommends how to remediate them. And if you think about this, if this is something that you're going to do as an individual, on one application that might be manageable. But as you scale and have multiple applications throughout your organization, you need to leverage something that's going to automate a big portion of that for you. Otherwise, you'll have developers solely focused on trying to go into the weeds on every single application. It's not really necessary, and Code Guru can help you with that. So let's talk about some of the resilient patterns we have today. Whenever one service or another service calls another, failures can happen. So if any of you have used an API, this is a great example. These failures can come from a variety of factors. They include servers, networks, load balancers, software itself, operating systems, or even mistakes that system operators might make, like me. Think back to that first time you had an outage. Anticipating these potential failures includes designing systems capable of reducing the probability of failure. It is, of course, impossible, and I really can't stress that enough, it's impossible to build a system that will never fail. But there are a few things that you can put in place systematically to help reduce the chance that it will fail. To build resilient systems, you should employ things that are simple, yet often forgotten. And the first should be obvious to you, but I'm surprised at how many people it actually does affect, is set timeouts. Did you know that many frameworks have default timeouts set, and those are set to infinite? If not infinite, many of them are tens of minutes or an hour range. This is hands down the most common type of failure that I've seen. And it's something that's really easy to fix by setting a smaller timeout. Second, backing off on retry. Not backing off is a sure way to get what we call a retry storm and a subsequent cascading failure. By the way, always set jitter when you're using your back off. And the idea here is that if you have a system that's making a request and it hits a wall and we say, hey, retry. Well, it's going to retry at a specific time frame. And what you see happens is all of these requests start repeating and repeating and repeating, and they start to get these retry storms of these high peaks of just your system being slammed again and again. By offering what we call jitter, you basically spread that load back out with some randomness. So you basically use an algorithm to set the retry at a random period. And it can make sure that the load on your system maintains even if there is a failure. So we don't have these random spikes that could potentially cause you to DDoS yourself. And so the idea there is to implement jitter. And naturally, you also want to pair that with limiting the retries. So you don't want to just have it retry forever. I would even go as far as recommending setting your max retry to just one. Like just one. In most cases, one retry is enough to be resilient to intermittent errors. Say it was just a random fluke. You retry again, usually it works. And the more retries you do, it might actually cause more damage to your system than good. Like I said, these retry storms are things trying over and over again. So retry once, and then if it fails, just degrade gracefully. And finally, limit the size of queues. Again, this is something that is often overlooked and set to default, but limiting the size of queues can help in that scenario. On the back-end side, the two most important things to protect yourself are applying rate limits to your APIs and load balancing. It's the best way to protect yourself from unexpected cascading failures. Since we talk about jitter, again, apply this to other areas too. So look at things like periodic work, so timers, cron jobs. Defaulting on the hour is often the best way to have all the cron jobs and timers start at exactly the same time, which can essentially overload your system if they all happen at the same time. So add some jitter to those and spread out that load. In fact, add jitter to all your work. It's not a bad idea. And if you want to learn more about how Amazon sets timeouts and implements retries, I highly recommend this article from Mark Booker, Senior Principal Engineer at AWS. He walks through the whole process. It's a very good one, and it's a part of our builders library, which I recommend you just reading the articles in there. This is Amazon's prescriptive way of showing you how we approach DevOps and building applications based on our own learnings. So let me explain this through an example. And I'll use our network load balancers here at AWS. So this is our wildly popular Elastic Load Balancer. We'll talk through this as a demo. Under the hood, the network load balancer runs on our AWS Hyperplane, which is an internal service embedded within the EC2 network. The AWS Hyperplane can handle configuration changes by using a workflow that's described on the left. So whenever a customer makes a change, this is basically a change to their network load balancer. The changes are turned into an event and inserted in a workflow that pushes that change out to all of the Hyperplane nodes that need it. They could then ingest that change and make that actually apply that change to the system itself. The problem with this push approach is that when there are a large number of changes all at once, the system may actually slow down. And more changes basically means more work. Now, when the system slows down, customers naturally resort to trying again and again and again, which again slows the system down even further. So this is why we're recommending something like on the right. And I'll dive into, there's a couple different things that are at play here, so I'll dive into those in a second. But basically on the right, the solution is a far more simple scenario. So rather than generate events, the AWS Hyperplane basically integrates customer changes into, for the nodes, the AWS Hyperplane basically pulls from an Amazon S3 bucket. So basically, we push that change to the S3 bucket, and then the nodes themselves actually pull from it. And so what I want to be clear is that when we look at things like when do we choose a push versus a pull, we want to push to systems that are larger than us. So in this particular scenario, if we have a push method and our agent is the thing doing the pushing, that means that agent is responsible for managing all those connections. It needs to be able to scale to handle that load. Like I said, if we have suddenly a large amount of changes, it's going to take time for it to own those changes and see them through to fruition. But if we put that onus on a system that's designed for that, like S3, our agent actually has to be lightweight or gets to be lightweight. Basically, we make sure that it can push to S3, and that's all it basically has to worry about. By shifting the ownership to the nodes themselves to do a pull, we make them individually responsible. So we're shifting that work and spreading it out over the entire system, reducing the overall performance hit that you would see on it. And then we want to take this a step further. So we want to introduce what we call continuous work. And continuous work is the idea of having this consistency on the system at all times. So it's a means of trying to avoid those peaks of performance hits. So the idea is that as these nodes pull from that S3 bucket, the configuration file that they're actually pulling is sized to its maximum size right from the beginning. And we want to pull this consistently every couple minutes. So there are basically dummy configuration slots that are in there that are waiting to be filled by the customer when they make their changes. But that constant work is one of the most critical ideas for building a resilient system. By fetching this over and over and over, even across hundreds of machines, the costs are far less in engineering time than the opportunity cost of trying to build something on the left, where we're trying to make this one agent far more robust. It's a far more simple solution to try and meet the needs of the customer. And so the idea is understanding when to use push versus when to use pull, and how do we implement continuous work to make sure that we understand the overall performance of our environments. So similarly, if you want to learn more about this, we have another article here. I highly recommend that you read it. It's by Colin McCarthy, who's a VP and distinguished engineer at AWS. The gentleman is absolutely brilliant, and this document goes through a lot of detail as to why you would want to leverage this type of solution. So another design that we want to take into consideration is anticipation of failure. It's limiting the impact. So I want to be clear, like anticipation of failure is a way of predicting what's going to happen. And part of approaching anticipation of failure is really focusing on how can we reduce blast radius? How can we limit the impact of specific failures? And one of the best ways to do this is what we call cell-based architectures. A cell-based architecture, there are multiple instantiations of a service that are isolated from one another. And these services are structures that are completely invisible to the customers at the end of the day. Each customer basically gets assigned a set of cells that's also what we call customer sharding. For those of you in the database area, this should be somewhat familiar. It's very similar in concept to database sharding. In a cell-based architecture, resources and requests are partitioned into these little cells. They're capped in size. And the design basically minimizes the chance that if there's a disruption in one cell, for example, one subset of customers, that it won't disrupt any of the other cells. And by reducing that blast radius to a given failure, we can actually improve the overall continuity of the system and availability of the system, and we can make sure that continuity of the service remains high. And so the idea behind this, we'll compare this to a standard architecture, is that for a typical multi-AZ architecture, you're going to have something like what you see on the screen on the left. You're going to have a region, there's going to be 3 availability zones, you're going to have some kind of load balancer that's going to load balance across the application layer of your application, and that can be an EC2 instance, a Java app running in a container, it could be any form that you choose to load balance. But the idea is that that application is then going to have some form of data layer, and that's going to be replicated over a set of those AZs. In a cell-based architecture, we don't have one for all, we have all for some. And so the idea is in that cell, you have all of these components that are needed for that customer's service to function. So moving to the right, that's where you're going to have that cell-based architecture. And the way this works is we can duplicate this cell over and over again and apply a thin routing layer at the top. So each cell can be addressed via the routing layer, and we can use things like domain sharding to help enable this. And this is something that can be very easily done with something like Route 53. And using cells has numerous advantages. Among such are workload isolation, failure containment, the capability to scale out versus up, and most importantly, because the size of a cell is known, once it's tested, we largely understand it. It becomes easier to manage and operate. So limits are known and replicated basically across the cells. And the challenge then becomes more about knowing what's the right size for that setup. And so we want to figure out, what's that balance? So smaller cells are easier to test and essentially operate, but larger cells are honestly more cost efficient and make the overall system easier to understand. Think of this in the nature of containers. If you have a couple containers, it's very easy to understand those containers. But if you need to sprawl that out to 100 or 1,000, it becomes much more challenging to manage. And so the idea is that you want to start with larger cells, and once you grow, slowly reduce the size of those cells. And automation is going to be key here for operating the cells. Like I said, I use the example of containers as one way of looking at this. You need some form of orchestration. Something's going to have to help you manage this. Now, I did mention customer sharding. So let's look at an example of shuffle sharding. So on the left, we've got a number of customers. So those are the purple icons, the cute little icons at the top. And then underneath, we have the cells. And you can see the cells in green, or the icons in green, are the primary cells. So that's where we're going to direct customers to. The ones that are gray and have a bed icon, that's the backup. So that's our passive node. And so the idea here is that we have replication between the primary and the secondary nodes. So we can ensure that, as changes are happening in the primary node used by the end customer, it's immediately replicated so that if there was a failure, it wouldn't have an impact on the end user. So let's look at this in the context of a cell failure. So in a cell failure, if we have these applications at the top, one of the cells fails, all of these customers basically get routed over to their passive node. So you can see in this example, the Jester gets moved over to cell 5, the Rabbit gets moved over to cell 4, and the Corn gets routed over to cell 2. But what you'll notice here is the Rabbit was actually already in cell 4. So this particular failure only affected the Corn and the Jester. And so the idea here is, let's talk about this in the context of mutability. So one of the best ways to look at this is using servers. So immutability is great in this regard. So upgrading a server often goes something like this. You log in, you stop the app, you upgrade the repositories, you do a library upgrade, you test some stuff. Sometimes you have to go through debugging. Oftentimes you're going to restart the app and basically hope for the best. And during this time, the system is basically down. And manual rollbacks are basically down. And the more often than rarely, these types of updates result in a failure that a manual rollback is required to basically be initiated. And that often has its own risks. So as these were and are still often standard practices, this is a common approach, and it's a common challenge that's felt by most customers today. But a less common practice is to document all of these changes. The solution to mutability isn't a process, isn't implementing change management. It's not doing, it's not trying to prevent any of this. It's just basically not doing it in the first place. And so the idea is, in the cloud, this is becoming more easy, where we don't actually have to go through this process at all. And we want to put it simply that immutable infrastructure is a model in which no updates, no security patches, or configuration changes happen in place in production. It's not that they don't happen. We want them to happen before they reach production. So if any change is needed, basically the idea here is a new version of the architecture is built and deployed into production. And the most common implementation of this is the immutable infrastructure paradigm and the immutable server. It means that if a server needs to be updated or fixed, a new server is deployed instead of updating the one that's already in use. And once it's deployed, basically, we simply update the routing mechanism. And so let's look at this in this context of, we provision the system, this immutable server, offline. We go through and install any of the applications that we need. We then go through and basically test it and make sure it's working. And if it's working, we simply update the routing. So the entire time, the customer is visiting the current version of the site And once we're ready and we know that the new system is available, we simply point them over to that. And if there's any failures, we can then automate the response back to the previous version because it's still up and running. And so this is often something you see with containers and serverless functions, and it should be somewhat familiar to you. And there are many benefits to immutable servers and immutable architecture. So there's a bunch listed here. I really just want to focus on two of them. The key thing is, by frequently replacing servers from a base that is essentially a known version, it's in version control, the infrastructure can be reset to a known state. And we can avoid things like configuration drift. If any of you are familiar with this kind of shift left mentality, where we want to get everything into configuration, we want to get everything into infrastructure as code, you've heard this from us for years. Those of you in the container space that are starting to adopt things like GitOps, this should be very familiar. Everything should be based off of that known version controlled state. And so this is one of the key benefits that immutability will provide you. And the second thing I want to focus on is changes are safer because they're the previous version that's working, like I mentioned, the previous version is still up. So if there is a failure, you can quickly roll back to it. And that last sentence really is what we want to focus on. And one of the best ways to help with that is canaries. And so we'll get into that in a moment. But first, let's talk about monitoring. Monitoring relates to the canary story. Monitoring means inspecting operating conditions and alerting when anomalies occur. So from a resilience standpoint, the first thing you care about is your deployments. And using monitoring can make them safe. So if we look at this in the context of a canary, canary deployments are part of the immutable architecture pattern. And it's used to reduce the risk of failure when new versions of applications enter production by creating a brand new environment, which is the latest version of the software. And then you gradually roll out the change to a small subset of users, slowly making it available to everybody if no deployment errors are detected. And the idea here is that we want to leverage monitoring to basically understand how that new environment is working. And so if you look at this in the context of CloudWatch metrics, you want to set that canary as though it was production. So you want to treat it like a production environment. It's going to have the same tags, it's going to have the same alarms, the same metrics on it. But because it's going to be in that same pool of resources, it's going to be kind of buried under the metrics there. So you also want to consider it like tagging it for its own canary set of monitoring. So you can pick it out of the crowd and understand what's actually happening on those environments. And so as you see the success there, you start to roll more and more of the customers over. And the idea here is that you can choose different patterns for how you do that load balancing. So you can use things like internal teams versus customers, paying customers versus free customers, geographic load balancing. So you can base it off of a specific region. If there's a region that has fewer customers or is in a saturated market, you can make the decision based on your business. And this pattern is also something that we use to deploy new versions of cells in a cell-based architecture. So it's a pattern that's consistent. And there's a couple different ways that you can do this in AWS today. We have a number of services here. The three on the right are directly integrate with AWS CodeDeploy, which is a service that makes it easy to automate deployments. And this application deployments can become more resilient. Now let's talk about responding. And so the idea here is that John Alspaugh, the co-founder of Adaptive Capacity Lab, said that being able to recover quickly from failure is more important than having failure less often. And this is accurate. I mean, this is what we want to get to. Recovering is not always a binary solution. Remember, we talked about this earlier. Production systems are often comprised of hundreds of dependencies. And so the probability is that something somewhere is already in a state of failure. We call this partial failure mode. And some services are also more critical than others. And we want to basically understand from a recovery perspective, what are the different operation modes that we need as a company? So at minimum, you need to define what your minimal or your normal operations are. So you just need to understand, like, what is normal for us? And from there, you also have to understand what is your minimum critical operations. And based on those two, you can get a better understanding of like what you see as your norm and what you can't live without. And there can be shades of this in between. You can have any levels of these, but these are the two you absolutely have to have. And then from each mode, you can work backwards and work on different recovery plans from short to long term. And while this seems trivial, oftentimes it's not implemented. And what this does is essentially when there's a failure, if you don't have what your known operations are and what your minimum are and a pathway there, it basically leads to that during an outage, instead of having a focused recovery where you have a plan, there's some operation components in there, you end up with something that's largely unorganized and oftentimes is inefficient. And it leads to prolonged outages. So it takes longer to fix things. And as we talked about earlier, automation is a critical part of this. So as we look to resilience, we want to leverage automation wherever possible. And it's not just for deployments, it's also important as a pattern for responding to changes. So things like leveraging this pattern let your architecture react in response to things like events. And an event is essentially a change in state or an update, or worse, a change in configuration that can occur in your environment. And this is something that's really important from the immutability pattern perspective. And so if we look at this from an immutable architecture standpoint, it looks kind of like this. So on the screen, we have an example where we have a policy that is monitoring an S3 bucket. And so this S3 bucket configuration basically determines whether it's public or not. And we basically monitor the configuration, and if there's an event that occurs that's triggered, we check to see the configuration value of that bucket, and if it's changed, it reverts that change and reapplies it to what it should be. So essentially setting the bucket private after it's been made public. And this event-driven pattern is an extension of that immutability architecture. And this is something that GitOps kind of follows. It's the idea that we have our known state in configuration or in code, we're monitoring against that, and we're also monitoring the environment. And these events that occur in the environment trigger drift detection. So in this example, we've changed that bucket from private to public. Well, that triggered this review. We then evaluate the proposed state, we see that it's different, and then we do this remediation step. And so that's the idea of GitOps largely. And it's all based off of that immutability architecture. So to hit the nail on the head here, mutability is one of the most critical attack vectors for cybercrimes. When a bad actor attacks a host, most of the time they're trying to do something like modify the host in some way. They're trying to change configuration files. They're trying to install their own applications. They're trying to change network ports. And the change means the architecture is largely compromised. And it should be isolated and replaced immediately. This is one of the reasons why, if you're running a container-based environment, if somebody logs into a container in production, kill that container. That is a compromised container. No one should be logging into production systems. If somebody is, you've got a challenge there. The immutability of that system has been compromised. So we want to make sure that we're detecting, isolating, and replacing instances based on that. And a big part of resilience is also being able to respond efficiently. This is something that machine learning can do very well and is informed by years of operations at AWS and Amazon. And we developed DevOps Guru. It's a machine learning powered service that makes it easy for developers and operators to automatically detect issues, to improve application availability and reduce expensive downtime. So this sort of ML powered tool is gaining popularity, and for lots of reasons. They help reduce noise, they bring to surface critical issues with relevant data and help identify causes quickly, and in turn it helps minimize time to recovery. So let's understand how DevOps Guru works behind the scenes. So DevOps Guru automatically ingests and analyzes metrics such as latency, error rates, request rates for all resources, and essentially it establishes a normal operational bounds. Remember, we said we wanted to figure out what the normal was. This is a way to figure out what normal looks like. And DevOps Guru then uses pre-trained machine learning to model that and identify deviations from that established baseline. So when it identifies an anomaly, it will go, when it identifies an anomaly, such as things like latency, error rates, or resource constraints that could cause potential outages or even service disruptions, it alerts the operators with issues, with the issue details like the resources involved, the timeline itself, so it sends the issue timeline, and other potentially related events that can help you quickly understand what is the potential impact of that. So it gives you kind of that full view of what's going on. And then once you enable DevOps Guru, it's going to start ingesting the operational data from the vended CloudWatch metrics. And it's going to use things like ML detectors to detect those anomalies. So here you can see there's a serverless infrastructure being monitored, which is based off of the CloudFormation stack. And once an anomaly is detected, it'll look up the CloudTrail logs, collect the events that are relevant to the anomaly, correlate those, and construct recommendations with prescribed guidance based on how to fix it. So it'll basically package all that up into what we call an insight. And this is how we enable the operator to identify the culprit very quickly, and they can take into consideration any corrective actions to recover. And that ultimately helps reduce the mean time to recovery, or MTTR. DevOps Guru also correlates and groups related applications into and infrastructure metrics like web application latency spikes, running out of disk space, bad code deployments, and memory leaks along the way. And it's going to help you identify and reduce false and redundant alarms so you can focus on the high sensitivity things. Like the idea is we want to get the eyes on glass on the right things on the glass, not the things that are going to waste their time. And so lastly, let's look at learning. And the idea here is that we want to show best how to learn from our failures. And so we want to take what we've done from anticipation, from monitoring and resilience, and figure out how we can learn how to better operate the solution. And one of the mechanics that we look at is what we call a correlation of errors. It's similar to a postmortem. And the process is where a team reflects on what happened. And so they look at a problem, and maybe it's an unexpected loss of redundancy, or perhaps something like a bad deploy. And we basically document what happened, what it was, and how we're going to apply a fix for it in the future. So there are 5 main sections in the COE document. So predominantly what happened, what was the data to support that, what was the impact potentially for internal teams or customers, what were the contributing factors, what did we learn basically from this, and how we prevent it from happening again in the future. We use this mechanism to learn from our mistakes essentially, and whether it's flaws in tools, processes, or even the organization itself, the COE mechanism is critical in identifying the contributing factors for failures, and more importantly, helps us understand how to drive continuous improvement. This isn't about pointing fingers and saying, you were wrong, this was your fault. It's really understanding what actually happened, how we can prevent it in the future, and how we can automate that. What can we do to learn from it and potentially grow together? And to learn more about this, there's a link on the bottom right. This is a talk from Becky Weiss, a senior principal at AWS. Highly recommend going through that. And finally, let's talk about continuous resilience in the context of chaos engineering. And chaos engineering is the process of stressing an application in testing or production environments by creating disruptive events, like things like server outages or API throttling. Imagine you've got a container cluster and you sweep one of the legs of the server nodes that are on there. And it's the idea of observing how the system responds to and responds and basically implementing resolutions for it. So chaos engineering helps in a couple ways. Especially for resilience and performance of your application. It looks to help you uncover potentially hidden issues and exposing things like monitoring, observability, and alarm blind spots. Things that you may have thought you had in place, but until you've done something to actually monkey with the system, so to speak, you identify those and you go, oh, we missed something here. And so chaos engineering as a practice gives an organization a platform to perfect operational skills that are critical, absolutely critical to building a culture of resilience and improving recovery time from failure. So to help you get started with chaos engineering, we have AWS Fault Injection Simulator. It's available in all commercial regions. It's easy to get started with, and there's no need to integrate multiple tools. You can use the AWS Management Console or the CLI, and You can use things like pre-existing experiments that we've kind of defined as templates to get started, and it's easy to share with others. So it lets you basically test real-world conditions, test using real-world conditions, and run those experiments in a safe manner in your environment. And you can implement specific safeguards to say, okay, this is a stop condition. Don't go any further here. So let's look at this in context. So the fault injection simulator utilizes, like I said, these experiment templates that can be created from the console or the CLI. These templates include a set of actions, targets, IAM roles, and any kind of stop condition or safe word that your environment needs. When you start an experiment, it will go through and perform actions against the targets you specify, such as stopping an EC2 instance or an ECS cluster, like I mentioned. It'll monitor the experiment through to completion. So it's basically going to look at the whole thing as well as monitor any of the experiments for their safeguards to see if it needs to stop something. And that's when a stop event occurs. And then you can, of course, hook up any kind of third-party monitoring here. So that's really all there is for now. So I want to make sure that you understand change takes time. The idea isn't to eat this elephant in one bite. We want you to implement these things slowly over time, and don't lose patience. As long as you trust in the process and see yourself growing and evolving, that's what resilience is really about. It's building that willingness to not fear failure, but embrace that failure, learn from it, monitor it, anticipate it, and continue to grow from it. And there's no secret sauce. So the real quality of how to achieve this high quality is based on habits. And paying attention to details, being paranoid with what could go wrong, and consistently thriving for improvements, you're going to find a way to make this reality. And if you want to go deeper into any of this stuff, we've got a number of different resources that you can leverage today. I'll leave this up on the screen for a moment, or you can pause your video and basically look at this. But we've got a number of different resources that can help you get started. And if you want actual training on this, our training and certification team offers a number of different trainings around DevOps. And so I want to thank you for your time. I really do appreciate you giving me the time of your day. I know there was a lot of other content out there, so I appreciate that you listened to me for today. If you have any questions on any of this, you can always hit me up. My Twitter handle is @BoringGeek, and I welcome feedback. I welcome questions. I'm happy to engage online. And thank you, and have a wonderful day.